So the first thing to notice is that the function so defined has to be a one-to-one function. We do not know its domain, nor do we know its range per se. The domain may be all of W1, but in the example I gave earlier, the domain is 1 through 4. We don't know. And likewise for the range, it may be all of W2, or it may be a proper subset. In any case, we would like to show something generic about f to use later on in the proofs. That is to say, we're basically going to prove a lemma inside of proving this theorem, which is that f is order preserving, if it is so defined. So, in order to do that, well, of course we need to have, assume that some element is less than another one and show that f preserves the ordering after mapping, basically. But f itself is defined in terms of isomorphisms of initial segments. So the way that we're going to do this is, in fact, to prove something kind of generic about all isomorphisms on initial segments. So, namely, suppose that we have two initial segments given by x and y respectively and an isomorphism h between them. And also suppose that we choose a lesser element x prime. Then it is very easy to just restrict h and argue that the resulting restriction is an isomorphism from x prime, the initial segment given by x prime, to the initial segment given by h of x prime. So what this does for us is it shows that x prime comma h prime is in the function f, right? Because after all, we know that the isomorphism there is an isomorphism given by the initial segments, so that implies that the pair of values is in the function. That's how the function is defined. Now, what that otherwise said, f of x prime is h prime. We know that h is an isomorphism and therefore order preserving, so we get to say that that is less than h of x. Now, one other thing that is not hard to show is that both f and h are isomorphisms. I mean, we assumed h was an isomorphism. It's not hard to show that f must be an isomorphism on the initial segments. We don't know that about f generally, but at least on the initial segments, it's easy to show that f is an isomorphism. We also know from an earlier theorem that isomorphisms are unique on well-ordered sets. So f and h must be the same function when restricted to these sets. That tells us that f of x is equal to h of x. Well, what we have now, in total, to put a bow on this, we have shown that if you assume x prime less than x, you get that f of x prime is less than, by chaining these together, f of x prime is less than f of x. That is just showing that f is order preserving. So that's the lemma. I'll end the video here and really get into the proof in the next video.